Okay. Good evening and welcome back. Let's start. Just before we start, last week I forgot to give you the attendance sheet. So I remembered a few who were here. So I already put some check at a few names for last week. But if you were here and if you don't have something next to your name, please add it and add it for tonight. I'm not very strict on this, but I just want to keep an idea about who is coming and who is not coming, more importantly. Okay, so what about last week? Okay, good evening. Last week, this is a quick reminder, we discussed and we will still discuss today rooted trees. So this is a tree with a specific vertex which we call the root. And I introduced the notion of siblings and internal vertices. Be careful, I was confused last week. Internal vertices are all vertices except the leaves. So the root is also an internal vertex. Then we introduced p-airy tree or p-airy tree, the notion of complete if everybody except the leaf have p children. And we had also this notion of ordered tree where you decide when you have children, which one is the first one, the second one, the third one, and so on. And with this, we define binary or ternary trees. So binary tree is a two-airy tree, which is ordered, and ternary tree is a three-airy tree, which is also ordered. They can or are not complete. It depends. In the definition, the completeness is not required. Then I just mentioned a few examples of the appearance of these structures in decision trees or in tree data structure. If you look at your computer, probably you have exactly this for your folders. Also the notion of short path tree. Then traversal, it's one way to visit all vertices of a graph. And for a tree, I introduced 4 types of traversal. So these, of course, you can do it randomly, just visit all vertices of a graph. It's probably not the best way to do it. So for trees, there are 4 systematic ways to do it. Of course, you can invent more, but at least I introduced 4 of them. Now, when you have a binary tree, you can discuss what is, and you fix a X, you can define a vertex X, you can define the left tree below X and the right tree below X. This is well defined for binary trees. And then the last section was about application. So I quickly mentioned what is an arithmetic expression tree. It allows you to write some formula without the parentheses by using the structure of the tree. Then if you want to organize some data which are fully ordered or totally ordered, and this is important, it means whenever you have 2 entries, you can say which one is the biggest one among the 2. So whenever you have a fully ordered set, you can define what is a binary search tree, which allows you to search for some information quickly. So there are some algorithms for searching the information, for removing one entry or for inserting one entry. But again, it's based on a totally ordered set. And finally, I introduced this Huffman tree and Huffman algorithm. It's one way to, if you have a set of symbols, let's say an alphabet, you want to assign to each letter a binary code or a prefix code. It's a sequence of 0 and 1. And there is a small difference between binary code and prefix code. You can always do it, but now you want to do it efficiently. So if each letter has a certain weight, for example, a frequency of appearance, you want to minimize the number of bits you need for encoding a text. So you associate a weight for each symbol, and then you define this weighted depth with a certain formula, and this Huffman algorithm gives you one way to find an efficient prefix code. It's not unique, the solution is not unique, but the weight or the average number of 0 and 1 you need for each symbol is unique. Okay, so this is what we did last week. Today we are going to first introduce a slightly different type of tree whenever you don't have a totally ordered set. You know, this is quite a strong requirement. It means you have quantity that you can always compare. But if you think about you have a big set and you take some subset, then this one and the other one can be compared because they are one into the other one. But for example, these two sets, which one is the biggest one? You cannot say. So you have, I'm going to explain, you have a notion of partially ordered. So some sets can be compared, but some cannot. And this happens quite often. You have data which sometimes can be compared, sometimes not. So how can you cannot do such a tree. If you think about it, it doesn't work because when we constructed the binary search tree, we really used the total ordering. Still, we can arrange the information in a tree which is less efficient, but still you can get something. So this is the first part. And then we are going to grow trees. Of course, at any time, you can interrupt me on the same for the students online. If you want to ask questions, just unmute yourself. So section 334, it's about priority trees. And as I just mentioned, the first thing I have to do is to define something which is less ordered. What is this kind of structure? Partially ordered. So this is the first definition. This has nothing to do with graph theory, but it's good to have this notion in mind. So a partially ordered set. A partially ordered. And I'm going to use just the same notation. But this is just a notation. Be careful, it doesn't mean this is the sign you use for numbers. It's just a set and what I'm going to, a certain relation that I'm going to define. So a partially ordered set like this consists in a set S and a relation which I denote by this sign satisfying for any ABC in S, so for any elements of S, they satisfy again three conditions, like for totally ordered set, but these conditions are slightly different. The first one is that A is always smaller or equal to A. Okay. This is nothing special. But the second one is if A is smaller or equal to B and B is smaller or equal to C, then A is smaller or equal to C, which is quite natural. This is called the trend. Sorry, this is already the number 3. So this is, sorry, I missed the 2. This is called the transitivity. And the example I have in mind is the one on the right. If A is included in B and B is included in C, then A is included in C. What about the 2? Sorry. Or maybe I put it below. But this, the number 2. The number 2 is if A is smaller or equal to B and B is smaller or equal to A, then A is equal to B. This is called antisymmetry. These are the 3 conditions that this relation has to satisfy. But you observe one thing, it's different from the totally ordered set. In the totally ordered set, I was always able to compare 2 things. The third condition was always A is smaller than B or B is smaller than A. There's nothing similar here. So it means it fits into this. The first one is just.
You have to define what is equal.
Okay. I don't define what means equality. I'm just considering a collection of objects. Equality means the two objects are the same. So just, I want to emphasize the relations A smaller equal to B and B smaller equal to A can both be not satisfied or not true. I'm not saying that we always have A smaller than B or B smaller than A. They can be both not satisfied. So it's a partial order, like this picture. So keep in mind this picture. This is the best example. Observe that if you have a totally ordered set, it's also partially ordered. So remark totally ordered set, like we introduced last week, are also partially ordered. So it means we are considering something bigger, a larger class of objects and relations. Okay, so I want to construct a tree related to this, or which can encode this kind of information. And this is going to be called a priority tree. But I need one more ingredient before this. The next ingredient, I will do a picture before introducing it because it helps. So I'm going to give a definition, but first I draw an example. Keep this in mind. We will check my definition based on this. And I will call this, we have levels. So this level is H. This level is H minus 1. This is H minus 2. It could be bigger, but we will see. So let me now introduce a slightly complicated definition, but not too much. A binary tree of height H. Remember, this is the distance between the root and the leaves. So I have a distance H is a left complete. The left complete tree if before we had the notion of complete, which means everybody has the same number of children, this is left complete if there are three conditions. For any x with d of Rx is equal to H minus 2 smaller or equal, then X has 2 children. So the first condition says until the H minus 2 level, it's complete. You have always 2 children. Until, so for any distance smaller than H minus 2, X has always 2 children. Okay. It's complete at least until h minus 2. They exist, remember this sign means they exist. They exist at most one vertex x with d of Rx is equal to h minus 1 and with one child. So at the level h minus 1, at most one has only one child. All the other one have 0 or 2. Let's look on this example at level h minus 1. Oh. In this case, yes. Oh, so is it correct? Sorry. No. Sorry, there is a small mistake in this picture. The height, this is h. Children are at h. This is h minus 1. This is h minus 2. Sorry. So the first line was fine for my picture. Now the second condition at level h minus 1, at most one vertex has only one child. It can have 2 or 0, and at most one has 1. And the third condition, no vertex x with d of Rx is equal to h minus 1 has fewer children than a vertex on its right. For vertex, let's call it y, with d of y is also equal to h minus 1. So let's check on this example. Take a vertex at h minus 1. What it is, the number of children is decreasing. That's a way. Check any x has, there is no x which has less children than the one on the right. So this one has not less because it's 2 on 2. This one has not less because it's 2 on 1. This one has not. Yeah, this one has 0, so this one, it's fine. And by the way, I should not have these lines also like this. So yeah, the third condition is satisfied. So it's not complete, because complete would mean everybody would have 2 children except the leaves. But we have this condition that only, the condition 2 and 3 are important. It looks technical, but it plays a role. So you can draw 1 or 2 examples, and at the end of the day, these conditions are not so complicated. It's only the first time you see them that they sound complicated. Now, what is a priority tree? So remember, I have this notion of partially ordered set, which I want to put in a tree. So a priority tree T, and remember, it always has a set of vertices on a set of edges. So priority tree T is a left complete binary tree. So we are exactly in the setting introduced here. And a function omega from V to S, like the priority trees. So there is a function from the set of vertices to S, but this time S is only partially ordered. Is S a partially ordered set? Such that now there is a condition such that for any x in V and any child y of x, one has V of and I just add one word because this is a word used. The elements of S are called priorities, are called. So in the notes, you can see one example of such a priority tree with intervals, because before I made this picture with sets, but you can think about intervals. So remark, when this explains the picture in the notes, the set of intervals in R is a partially ordered set. And what is a partial order? Take an interval AB. You're going to say that AB is smaller than CD. Be careful, these are intervals. If AB is included in CD, and take an example, take two intervals, 0, 1 is included in 0, 2, for example. Example. 0, 1 is included in 0, 2. As intervals, these are not just pairs of numbers. So I just wanted to explain that intervals are partially ordered sets. It's a partially ordered set. So you can build a tree. Let's say I take 0, 10. Then I'm going to take 1, 8. And indeed, 1, 8 is included in 0, 10. Then I can take, let's see, 2, 3. And another one, which is 4, 5. And you see here, these two children are not comparable. And for example, here I could take 4, 7. There is no contradiction. It respects what I mentioned. And so what is now there is an exercise, which is not an easy exercise, and probably my notes are not good about this. So I encourage you to really work on this exercise. Create an algorithm for searching in a priority tree, but also for, it's a second question, for removing one vertex and for inserting. And why it's not completely trivial? Because of course you want to keep the structure. You don't want to start again from scratch. So if you want to remove this guy, you need to do something. How? Of course, here it's rather simple because you only have two below this one. But how can you arrange to remove this one? And in my notes, I realized that what is written is for totally ordered. For totally ordered, it's easier because you can always compare. The same for inserting. How can you insert a new interval? I'm not saying it's easy, and probably there is a trick. And I didn't search for a long time, but I didn't find a clear algorithm on internet or in a book. But of course, you can find something. Maybe you need to insert, so just an idea. I don't know if it is useful, insert. Let's call it a universe. What do I mean by this? You know, if you want to insert the interval 111, you have a problem. Where do you insert this one? Because it's not comparable. Oh, no, 111 is fine. Sorry. I should take. No, 111. Yeah, because it's insert. Let me take. Oh, no, 111 was okay. I start at 0. 111 is okay. You cannot insert in this. So probably you need to build a slightly bigger tree, and the root should contain both. Should contain this guy and this guy, because it has to be bigger. So you probably, if you write the algorithm, the price to pay might be, okay, I add an element which is bigger than anybody. This is what I call a universe. Somebody which is bigger than everybody. Otherwise, I don't know how you can insert a new vertex which has nothing to do with the other one. Probably you want to add it here, but this is not a tree. So probably you need to do something like this. So try, again, it's certainly not trivial. And if you do it well, it's certainly interesting. Try to find what is a searching algorithm for finding if an interval is contained in such a tree without checking everything. Of course, you can check all the entries, but this is not efficient. So searching is rather easy if the tree is already built, but then removing or inserting. In my notes, there is something, but it's probably only for ordered set, purely ordered, totally ordered. So this is an exercise which is related to algorithmic, and you don't need any specific tool for this, just think about it. And you can wonder, or it's no more in the definition, why you need this left complete structure. You will see in my notes, this is useful for inserting new elements. You can use this structure for inserting elements in a clever way. So it's not for free that the structure is given. And I'm not sure that this is fine either. Okay, this is an open question. I don't have the answer. So think about it. Any question or remark? Again, this is open, but I think it's interesting. 3.5, a very short question. And it also contains some questions. So somebody asked me about subject for report. This is a nice subject for report. Counting trees. This is linked to combinatorics. So two basic questions, and they are not trivial, but they are quite natural. How many different, what do I mean by different? It means non-isomorphic. Non-isomorphic binary trees with n vertices. Let's say this is the first question. I will make a picture, but let me directly state the second question. So this question is if you want to compute something or do many drawing. Second question, how many? Again, non-isomorphic. Three. With n labeled. What do I mean by labeled? I mean, you give a name, the vertex 1, the vertex 2, the vertex 3, or you put colors. In the notes, you have one picture with colors. These are the trees with colors. So for two vertices, 2 vertices, 3 vertices, and 4 vertices. How many trees which are not isomorphic? I mean, if you can just rotate and get the same tree, they are isomorphic, so you're not going to do it. But how many different trees with labels, so with either colors or numbers, can you build? It's not trivial. Of course, you can find the answers on internet. I'm not saying you have to do from 0, but you can think about it. I'm just going to give you an idea about the first question. The second one, I can give you the answer. And it's written in the note. The answer is, the solution is n power n minus 2. But of course, you have to understand why. But you can already check for n is equal 1, 2, or 3, or 4, it's rather easy. It's not a tree. So n is equal to 1, you take it as a definition. So yeah, n is equal to 1, you don't have any tree. So, okay, n bigger than 2, bigger or equal to.
What if, like, they are two? So, for example.
No, but this question is especially for labeled one. The non-labeled is more related to the first question. I'm not saying that these are the only questions you can construct or you can build. There are many questions, but I just mentioned 2 of them. So let me give more information about the first one. And we will count for n is equal to 1, 2, or 3. And I will give you the way to solve it. So the first question for 1. So I call Cn the solution for n vertices. So let's check. C1, I take as a definition, C0 first. C0, I take it as a definition. It's 1, you will see why it's convenient. And the same for C1, I just fix it equal to 1. This is just a convention. Now, what about C2? So we are looking at binary trees, which means children are ordered. So they are either left child or right child. So for two vertices, we have this or this one. They are not the same, because here you have a left child, the other one you have a right child. So C2 is 2. Now C3. Things are more interesting. One easy one is this one. One left child, one right child. Another one is two left child, or two left children. Like this. This is one more. Then we have this one and this one. They are not isomorphic, because you can check the isomorphic should preserve if it is left or right. And so you cannot create an isomorphism. So it means C3 is 5. How can you do the general case? You can do it by iteration. So suppose, what about Cn? I want to build all trees with binary trees with n vertices. So I'm going to use induction. So we have this part, remember, or maybe, no, maybe it's, should do it like this. This part and this part, this one, if I call this x, this is Lx, remember, and this is R of x. So I would like to compute Cn based on Cn minus 1, Cn minus 2, Cn minus 3, and so on. So there are different possibilities. Lx, suppose it is 0. Well, 0 vertex. Then it means, okay, I should not even draw this, but I started to, so, okay. With my definition, Lx should be a tree, so, but, okay, I should do it like this. If Lx doesn't contain anybody, then how many solutions I have on the right? No. Then Rx, how many vertices contains n minus 1 vertices? Because 1 is used for the root. And for n minus 1, we have Cn minus 1 solutions. Because it has to be a binary tree. So we have n minus 1 ways to construct this binary tree with n minus 1 vertices. Think about it. But of course, this is only one possibility. Now I can also have L of x is 1 vertex. So now I have only one vertex here. So on the right, I have n minus 2. So if L of x is 1 vertex, on the right, we have C n minus 2 possible trees. Think about it. You use 1. 1 is used for the root, so you have n minus 2 ways, n minus 2 available vertices, which means you can build Cn minus 2 binary trees. So it means, what is the general relation? So now Cn, so in general, Cn is given by 1 times Cn minus 1. This is the first possibility. Then you have plus 1 times, because with 1 vertex, you have only one solution. plus 1 times Cn minus 2 plus, and now it's more interesting. If L of x contains two vertices, we already know we have this number of solutions for the left, and for the right, you have now n minus 3 vertices available. So you have to do plus C2, no, C3. Wait. Oh, sorry, so I said something wrong. You have only two ways with 2. So it's C2 times Cn minus 3 plus then C3 Cn minus 4. Why it's a multiple? Because you do 1 tree here, and then you have all the other one. Then you change this one, you do all the opportunities here, and so on. So it's really a product. So and you observe now, this is C0, this is C1, and this is why I use this convention. So it means the total number is sum j from 0 up to n minus 1 of Cj C n minus j n minus j minus 1 probably. Yeah. All right. So if you have time, you can compute these numbers, because we already did C3, so you can do C4. It's just a sum, and then once you have C4, you can compute C5 and so on. Of course, it's not the fastest way, but it's one way to compute successively all Cn. And if you use an Excel sheet, this is done in 1 minute. I mean, you just put the formula, you check it, and you can solve it. What is and this has a name. This is called Catalan recursion, because Catalan was a mathematician. This is called Catalan recursion. And I can give you the solution. Cn is this is a combinatorial. Again, I'm not saying that you have to find this by yourself, but you just Google a few keywords and you will find the solution. And your job then is to understand this solution and to write a report that is understandable for everybody. So now you have at least 3 possible reports, one about the first question, one about the second question, and the one about the algorithm I mentioned. The algorithm is not trivial. You can work by pair or 2 or 3 students. There are a few more things written in the notes. So what I want to emphasize that trees appear at many places, and we can play a lot with them. You have a question?
They also appear in different pairs of number pairs.
Yes, these kind of recursions and these kind of numbers appear indeed at many places. It's not the only place where you will find such a relation. Oh, yes, then you can also write a report at different places where this relation appears naturally. This is also possible. So now you have at least 3 reports. By the way, I encourage you, if you haven't written anything, do it on graph theory, please. If you find an exotic topic which just use epsilon of graph, this is not the best solution. So please concentrate on something related to graph theory, at least for 60% of the material, at least. Okay, chapter 4, spanning trees. This is a very useful notion also, spanning trees. Let me first just draw a picture and then I will give a definition. You have a complicated graph. a spanning tree is going to be a tree which contains all vertices. So you start at one point, and you start building a tree. So you have to be careful. Let's see this, and this, and this. You can check the yellow is indeed a tree. Remember, one characterization of a tree that there is no cycle. And indeed, this has no cycle. The yellow part has no cycle. And it covers all vertices. And again, it will be useful for searching in some structure. So we are going to work today on these spanning trees. So section 4.1 is how to grow or growing trees. We're going to grow trees. And be careful, this is the easy picture. It can also be a oriented graph. So if we have orientation, we need to be a little bit more careful. Okay, so let me give you a definition of a spanning tree. And Kato-san, if you're online, you worked on spanning tree for a while. Definition. So at the beginning, I started with just a graph. So let G be a connector. I want it to be in one piece, one connected group. Of course, if you have two pieces, you cannot just construct one tree. So we start with a connected group. A spanning tree T inside G, it's a tree inside G, is a subgraph of G, which is a tree, and it has to contain, which is a tree, I have to be slightly more precise, either undirected, if we have no orientation, or an arborescence, if we have orientation. Or arborescence, which contains, let me continue there, it contains all vertices. So, which contains all vertices. Of course, of G. So it means arborescence, remember, it means if we have an orientation, the orientation has to be always from the root, this is the root in this case, from the root towards the children. So this would be an arborescence, right? Be careful, and it's clear, not unique. Maybe in some, no, except if the G is already a tree, probably in all other situations, you have more than one solution. Just think about it, except if it's already a tree. So you have more than one spanning tree. And so this is the first thing. For indirect tree, for indirect graph, undirected graph, do you think it always exists or not? You're not supposed to answer immediately, please. You have at least 3 years or 5 years older than all the other students. Okay, yes. The answer is yes, it always exists. How can you check it? Just try, and you will see that it always exists. Secondly, give a proof, which is an easy proof that it always exists. So for undirected graph G, a spanning tree always exists. It's not difficult to see why. You just start doing some pictures and then you realize that you can always do it. Now for directed tree, or for when you have an orientation for directed tree, for directed graph, it most likely does not exist. This is not a precise statement, of course, but build any graph. Oh, build any graph with orientations. Okay. And try to see if you can build. Oh, in this case, yes, it's possible. There is one solution. I think if I start, let me check. If I start here, I have this one, this one, this one, and this one. All right. So in this case, this is an arborescence. You have it. But it's more difficult. If I change at one place, probably it will not work. So I found one which works, but just check. Most likely, it will not exist. But
erase the bottom right one.
Then if I erase something, it's not the same graph.
I mean the yellow one you drew, the bottom right yellow one, even if you erase that, I think it's still a sign.
If I erase what?
Yellow bottom right.
This point?
No, the yellow line between that point and the.
But
erase that, is that still a spanning tree, the remaining 3 yellow lines?
No, if I erase. Oh, yes, you're right. I did a mistake. Okay, you're right. It was not, it was a cycle. There was a cycle. Yeah, there was a cycle. So this is correct now. But yeah, this one by chance has a solution.
Rerun this, you can.
But if I change, yeah, but if I reverse indeed some arrow, probably you're not sure. Maybe you have it depends. There is one question which I don't fix is, do I fix the root a priori or not? And it depends on the problem. If you tell me, oh, the tree has to start here, then it's a very strong constraint. If you tell me, oh, you can start anywhere, then first you have more trees to build, and probably you have more options to get a spanning tree. So these are two different problems. Do you fix the root or not? It depends. Okay, but now we know what is a spanning tree. It's a tree which is either undirected, or if it is directed, it has to be an arborescence. But now the question is, if you have a complicated graph, how do you build such a tree? And as we said, they are highly non-unique. Is there a better one, or it depends on what you do, but can we find an algorithm for constructing a tree which has some additional properties? So this is what we are going to discuss. But before we discuss this, I have to give you a few more definitions. Again, if you have any question, you can interrupt me at any time. So let me start a few definitions. So G, a connected graph, and T, included in G, a tree. I'm not saying that it's already a spanning tree. I'm just saying we have a tree inside G. So what are the different notions? A tree edge. A tree, this is quite natural. What is a tree edge? It's an edge which is in the tree. Or a tree vertex. An edge. Or a vertex belonging to the tree. This is quite natural. Yeah. Got a graph and got a tree inside, then you call a tree edge or a tree vertex either an edge or a vertex which belong to the tree. And obviously a non-tree edge and a non-tree edge and non-tree vertex. And I let you finish the sentence. It's clear. Either an edge or a vertex which do not belong to the tree. Okay. This is the first part of the definition. Something more interesting. What is a frontier edge? Frontier edge. So probably I should do my picture again. I do it undirected because it's slightly simpler. And I built a tree, so let me build this tree. This is a tree, it's not a spanning tree, but still it's a tree in yellow. So what is a frontier edge? Is a non-tree edge, so it does not belong to the tree, but with a certain property, with one endpoint in T and one endpoint not in T. So let me draw one tree edge, for example, one frontier edge, for example, this one. This is an example. This is a frontier. It's not the only one, but I want to keep my picture simple. This is a frontier edge. Be careful, this one is not. It doesn't belong to the tree, but it has the two endpoints in the tree. This is not a frontier edge. Okay. Now, if this is without orientation, if the graph is oriented, so it's still in this point, because remember my aim is to grow a tree or to grow arborescence. So if G is oriented, a frontier edge, satisfies. So remember, for when it's oriented, we have an origin on a, so we have an origin and a target. So I specify it satisfies the origin, frontier edge E satisfies the origin is in the tree and the target is not in the tree. So on this picture, if we have an orientation, it should go like this. The origin is in the tree, the target is not. Otherwise, it's not a frontier edge. Okay? This is for oriented tree. And the set of frontier edge is denoted, I'll give a name by font. It depends on G and it depends on T. So I need to give a name. So now if I come back to the situation here without orientation, if I want to draw the set of frontier edges, we have this one. This one is one. This one is also a frontier edge. and this one. So we have 4. Because they're all connected to the tree at one endpoint, but not at the other one. Do you have any question? And if we have orientations, the set of frontier edge should be always with the orientation like this. If by, let's say, if this one, now I put orientation, if this one goes in this direction, then it wouldn't be a frontier edge. Okay. So now we have enough definitions. Remember, my aim is to grow a tree. So small lemma, small statement, which is easy. So G connected T inside G a tree. A tree either unoriented or an arborescence. And E belonging to this set front of GT. So if I deal with oriented, my picture should be like this. And maybe we have an orientation. What is T? I could write T plus E, but this is not the correct notation. But you can think about what is T plus the new edge. The correct notation is T union E. And I will even introduce a new notation, which maybe you haven't seen. A union, but with a square U. Do you know what it means? It's a union, but it means a disjoint union. You know, whenever you have two sets, the union is a union. But if you want to say that these two sets had no intersection, you can say the union, but of two disjoint objects. So this is called a disjoint union. Disjoint. So it's a union, but you give one more information. You say that before they were completely disconnected, and indeed the tree E is not in the tree. So there are two disjoint things. So what can you say about T union E? It's still a tree, or if there is an orientation, it's an arborescence. It's a new arborescence because I'm adding something which goes in the right direction. Right? So the statement is this new object is, so this union is either a tree, if it is undirected, or if it is directed, or an arborescence. In the case it is directed. And now you understand why, when I define the notion of front, if the graph had the orientation, I only consider the one starting at T, starting in T. Because if I add one edge, I get one more, a bigger arborescence. Okay. So this is a way I can at least grow a tree. But of course, I want to do something better. Just an observation, which is a trivial observation. But don't do this mistake. Front of GT this initial set is usually not equal to the new one. Front of, no, it's always different. Why is it always different? Because one edge was in frontier and is no more in frontier. So they're always different. And now, if you, now I have added this new one. Of course, I need to compute the new set, this new frontier of, and for example, I'm sorry for one, but this one is no more a frontier edge. On the other hand, this one is still, and I haven't, so let me draw the new frontier. This one is one, and I have, no, this one, I cannot, it's not a frontier because it would have two endpoints in the tree. So I have only one new. This is the green one. So just an observation, when you add one edge, of course, the notion of frontier is different. Any question? No, no, you cannot say this because, for example, assume I have many things here. Then they were not accessible before I added this one. They were not accessible, and suddenly they're accessible. So you cannot conclude about the size. No, there is no relation.
Question is to make that observation useful. What should be compared? It's not these two, but
wait a second. There, you know, I decided to add this one. Is it the best choice? We had three solutions. So which one is the best? And now it depends on your purpose. So whenever you have a choice, you have to justify it or justify why you take a decision. So we are coming to this. So it's just a remark which is not precise. When growing a tree, the choice of E inside this frontier of GT leads to different algorithms. So I have to be more precise. But what is the idea? How I'm going to choose the new edge? I mean, the rule I'm going to impose for choosing this new edge will lead to a new algorithm. So I will present two. Any question? So again, my aim is to grow a spanning tree. Think about unoriented tree or unoriented graph, because in the oriented case, sometimes you cannot grow a spanning tree, so it's less interesting. But so I start with one algorithm, the simplest one, which is grow a tree. So we are always in this setting G, connected. I don't specify if it is directed or not, but it's a connected growth. First thing to do is fix a root, except if it is given. If somebody tells you you have to start X at this point, but fix a root X0. And I'm going to set T0 is a tree just containing X0. And I need a counter I, which is 0. I fix a counter at 0. Okay. So maybe I should do a graph. I fix a root X0. Or somebody tells you you have to start from here. Now the second step, and I will make it more precise later, choose X, no, sorry, E, not X, E. Choose E I plus 1. It's going to be recursive, so that's why I put I. Choose I plus 1 inside the set front of GTI, set Ti plus 1 is Ti plus union E I plus 1 and I equal to I plus 1. So please understand the last condition as it should be. Of course, I cannot be equal to I plus 1. It means your counter, you add 1 to your counter. So what it means, at these steps, of course, if I start at 0, this would be T0, but I do it recursively. So I have a tree Ti inside the graph. I choose one edge inside this frontier, and I grow the tree with this additional edge. I call the new tree Ti plus 1, and the counter is now at I plus 1. Or I fix the counter. And the third point is repeat 2. Repeat the point 2 until this front of GTI is an empty set. When you have nobody in the frontier, you cannot grow anymore. If it is an undirected graph, it means you finish your work. If it is a directed one, it means you cannot go further. Either it's finished or simply you cannot grow the arborescence anymore. So it depends. Please be aware that for now, I just wrote choose. I need to be more precise, but you can do it. There is no precise way to do it here. Later, I will be more precise at this point. But please do a picture, either oriented or unoriented one, and try to check that you can grow a tree like this. So this works for undirected graph. And not always. Or directed. What I mean by it works, it means you get a spanning tree. This works means get a spanning tree. If it is undirected, you'd indeed get a spanning tree. If it is directed, it depends. And I did not mention it, but finite. Because if you take an infinite one, your algorithm will probably never finish. So take a finite graph. So let me emphasize, there are two things. First, I didn't say how to choose. You can always do it. When you have a set, you can always pick one, but there is a clever way to do it. And observe one more thing. I'm giving a name. I could write just choose E in this set, but I give a new name. I give a name. Choose. You give a name. I choose one and I give a name. I call it EI plus 1. So observe this. And I need to emphasize because it plays a role. Remark. In the second point, when choosing an edge, we give a name to it. We give the name EI plus 1 to it. And I just, yeah, I mean, I give a name. This index I plus 1 is called the discovery number. And it's important, the discovery number of the new edge. And there is even a function, it's called DF number, or this discovery number. DF number of this edge. You keep in memory the which index it has. This new.
I think it should be Francia G T I union disjoint union with I plus 1, like the Francia.
Here.
No, the next step.
No, it's correct. If at this step you don't find anybody, then you cannot add any new edge. So you, indeed, in fact, you have finished and you try next time and then you observe, oh, but I cannot continue because it's already an empty set. So you're right, you could maybe stop one step before, but okay.
I think this idea is to make sure the computer works for this. You should do this checking before the second.
No, because if you do this checking at each step, you're doing it too many times. If you implement it just at the next step, you do it only once. So I don't want to check every time if this is not empty and then continue. I accept that maybe at one point I will have an empty set and I will observe that at the next time I have this empty set, so I cannot continue. But I check it only once instead of checking every time if this is empty or not. So it's probably better. Okay, so I introduce this DF number. And I'm going to we also set X I plus 1 for the non-tree vertex of the new edge before adding it to the tree. Please think about this sentence. Once you have chosen the new edge, you call its endpoint, which is not in the tree yet, Xi plus 1. Then once it is in the tree, you don't have any non-tree vertex. Yeah, non-tree vertex. But just before you put it in the tree, you just give a name to it. Okay. Yes, now I can give an example. Yes, example. I want to reproduce the same example because otherwise I will get lost. Okay, this is a graph. I make one more vertex. Okay, and now I'm going to start at this point. So I call this X0. This is X0. Then I need to choose the first. I don't draw the frontier edge, otherwise it would be too messy. I just choose one. So I'm going to choose this is E1, so it means this is going to be X1, right? And so let me build the tree. We have X0, E1. And so this is X1. Then I need to choose a sec. Maybe I put colors once they are used. These two vertices are used. Then I need to take a E2. I'm going to decide that this is E2 because it's still in the frontier. So it means that this is X2 and observe X2 with E2. Then I need to choose a E3. So I'm going to choose, now this is, I'm going to choose E3 here. It's not completely random, but it's for a certain purpose. So it means this is E3, and we have X3. Then I need a, or maybe I can put in yellow. This was E1, E2, E3. Now I need X4, no, E4 first, E4, and this is going to be X4. So this is E4 on X4. Okay, and it's here. And now I need a number 5. Where is it? I'm going to choose this one. This is E5, X5. And probably I have everybody now. And so it is E5 on X5. So on the right, we have the tree corresponding to the spanning tree inside. Okay. What we observe, when I did this picture, I used the ordering, the DF number. Why? Because look, I started with this one and then this one. That's why the first one and the second one. Then starting from X2, I draw E1, E3, which is the only child. And then I have 2 children, but I first use E4 and then E5. So I create a binary tree. No, not binary, sorry, ordered. This is an ordered tree because I can do it because of the information about the numbers. But still observe that we have a few more edges. So which one are not used? This one, and this one, yes, and this one. Let me draw them just artificially in the tree because they have a certain meaning. So if we have one between X1 and X2. So one between X1 and X2, it is this one. We have one between X0 and X3. X0 and X3, sorry. We have one between X1 and X5. One between. And the last one is which one? X0, X5. Yes. Can you see that there are 2 types of these edges? You have 2 kinds. They are not exactly the same. And I will give a name to them. Look, some are in the same family, some are not. These 2 are from one ancestor to a child, or to a descendant, more precisely. from an ancestor to a descendant. On the other hand, this guy and this one, they have no relation. They are not in the same family. It plays a role later. So let me give the definition of this situation. And by the way, I already give the name. These one are called skip edges, while these two here, the two here and here, so we have two skip edges in this picture, and we have two called cross edges. So let me give the definition of skip edges and cross edges. A skip edge connects two vertices with one, the ancestor of the other. And indeed, this is what I represented on the right. And now, so this is a skip edge and a cross edge. A cross edge connects vertices which are not in the same family. Same family. Probably I did not introduce the notion of family, but you can guess. They have no common ancestors. And so far, so good for undirected graph. I'm not going to write it, but if you have a directed graph, you could decide to give a different name if a row is going from an ancestor to a younger person, or if it is going from a young person to an ancestor. So you have this notion of oriented skip edge and going down or going up. But I don't do it. Probably I wrote about this in the notes. Okay. So I haven't introduced yet a way to do it in a clever way, to choose these vertices in a clever way. I will do it next time. But we already observed that once we have chosen a spanning tree, the remaining edges can be divided into two types, and they play a role. One, which the type where the connections are within the same family, and the ones which are crossing between two families. This is the only options you can see. So next time we are going to see two algorithms which precisely depend on how we choose the edge in this frontier family. All right? Yeah.
They have no common ancestor, but isn't the root a common ancestor?
Yeah, but please read the definition of a skip edge. One has to be the ancestor of the other one. So one endpoint has to be the ancestor of the second endpoint. Of course, everybody has the same ancestors. The root is the ancestor from everybody, for everybody. But this is not the point. One edge point is the ancestor of the other endpoint. One endpoint is the ancestor of the other endpoint, while it is not the case for front edge. This guy is not the ancestor of this one is not the ancestor of this one. And the same, if we look X1 and X5, they have a common ancestor, but one is not the ancestor of the other one. So please read the definitions. Mathematics or any subject, you have to read the definition carefully. If you don't, you can speak about anything. and ask so many questions. Okay, any question or any remark? Or if you have online any question, you are also welcome to ask.